Welcome to our discussion on the mole. So, in this discussion, we're going to be talking about not the mole that burrows in the ground, not the animal mole, but we're going to be talking about the science mole. The science mole is a unit of measurement that we use to measure very small things. So, let's go ahead and get started. Let's talk real quick about just atoms in general. How many atoms do you think are in a single grain of NaCl, of table salt? So, if you did a previous activity, I had you measure out 12 grains of salt. Now, is that one single atom or is that many atoms? And if you're saying to yourself, that's many atoms in one single grain of salt, that's many, many atoms. And it's hard to just pull out one single grain of salt, right? And if you found the mass of that one single grain of salt, if you found that mass at a school, you would end up getting a mass of zero. But we know that it doesn't have a mass of zero because we know that there are atoms there. We know that there's at least one Na and one Cl atom, but really, in general, like we know from our previous knowledge, our background knowledge in science, that atoms are so much smaller than that, even. So there are many atoms in that one single grain of sand, of salt. So when I'm looking at these shoes we buy in pairs. So a pair of shoes, we buy dozen eggs. So we buy eggs in a dozen. What about paper? We buy paper in a ream. A ream of paper is 500 sheets, and a gross of pencils is 144 pencils. When you have a dozen of something, no matter what you are talking about, you know that you have 12 of that thing. So if I have a dozen donuts, I have 12 donuts. If I have a dozen eggs, I have 12 eggs. If I have a dozen cars, I have 12 cars. And if I have a dozen chemistry problems, there are 12 chemistry problems. So the mole is the same exact concept. Just like I have a dozen, and when I tell you, go to the store and buy me a dozen apples, or buy me a dozen bagels, or get me a dozen eggs or a dozen donuts, I know that you're talking about 12 when you tell me a dozen, or when I tell you a dozen, we know we're talking about 12. So when I have a mole of eggs, I have a number of eggs. It's a very, very large number of eggs, but a mole of eggs is 6.02 times 10 to the 23rd eggs. A mole of donuts is 6.02 times 10 to the 23rd donuts. A mole of cars is 6.02 times 10 to the 23rd cars. And a mole of chemistry problems is 6.02 times 10 to the 23 chemistry problems. That's so many chemistry problems, you wouldn't be able to do them in your entire lifetime. I wouldn't be able to do them in my entire lifetime. So when we talk about a mole is much bigger than 12. It's 602 sextillion. Okay. So obviously, a mole of chemistry problems is way too many problems, but obviously, this is a very big number. We're talking about a very large number. If you tried to count to 602 sextillion, you'd be counting forever. You'd probably die before you even got to that number. The mole is typically used for counting or grouping very, very small things like what? Like atoms. Atoms are so small. So scientists needed a convenient unit to measure microscopic matter or atoms and make them apply to our macroscopic world. Because think about the last time you made something at home. You made something in the kitchen. So say you were baking your favorite recipe of cookies. Okay. And you're measuring out a teaspoon of this, a tablespoon of that, all of that in that recipe. You know, I need this amount and this amount and this amount to go together to make this perfect recipe of cookies. Okay. It's the same thing with chemistry. In chemistry, we have chemical reactions, and we need to figure out how to measure our chemicals to make them go together to form this perfect recipe, this perfect product in the end. So, some random mole facts, and these aren't things that you need to remember, but just to kind of give you perspective of how large a mole is or how big that number is. One mole of moles, the animal mole, would stretch from the earth to the nearest star more than 2 million times. One mole of marshmallows, if I put a mole of marshmallows to cover the entire United States, that would cover the entire US to a depth of about 600 miles. One mole of rice would cover the land area on Earth, all of the land on Earth, to a depth of 75 meters. So think about what a meter stick looks like, okay? And if you don't know, check it out the next time you're in class. But a meter stick, or let's look at it in perspective, a meter stick is close to a yard, okay? And so 75 meters, that is close to 75 yards. That's almost a full football field covered in a depth of rice for the entire land area on Earth. Okay, 6.02 times 10 to the 23rd pennies, or a mole of pennies, would make at least 7 stacks that would reach the moon, from the Earth to the moon. A mole of grains of sand, or 6.02 times 10 to the 23rd grains of sand, would be more than all of the sand covering Miami Beach. And 6.02 times 10 to the 23rd blood cells would be more than the total number of blood cells found in every single human being on Earth. That is a huge number. So a mole, and its abbreviation is MOL, which is kind of silly. But a mole is the SI unit that allows us to count small things. It's the SI unit telling us the amount of particles that are present. So it can tell us the number of atoms, it can tell us the number of molecules, and it can tell us the number of formula units. Remember, atoms are just your atoms from the periodic table, your elements from the periodic table. Molecules are your covalent compounds. Formula units are your ionic compounds. And a mole is this unit that allows us to count these things without actually seeing them because they're so microscopically small. Okay, now we call all of these things representative particles. So what are we representing? Are we representing atoms? For copper, we're representing atoms. For molecules, something like that would be like sugar, C12H22O11. That's going to be a molecule. Or something even smaller like H2O. That's going to be a molecule. The representative particle for H2O is a molecule. The representative particle for NaCl is a formula unit. So 1 mole is 6.02 times 10 to the 23rd representative particles. So 1 mole of atoms is 6.02 times 10 to the 23rd atoms. 1 mole of molecules is 6.02 times 10 to the 23rd molecules, and 1 mole of formula units is 6.02 times 10 to the 23rd formula units. This number is called Avogadro's number in honor of the Italian scientist named Amedeo Avogadro. So 1 mole of anything is 6.02 times 10 to the 23rd. 1 mole of atoms is 6.02 times 10 to the 23rd atoms. 1 mole of molecules, 6.02 times 10 to the 23rd molecules. 1 mole of formula units, 6.02 times 10 to the 23rd formula units. And that's Avogadro's number. And that's why on Mole Day, we celebrate Mole Day on October 23rd. Can you imagine what time we celebrate? We celebrate from 6:02 in the morning until 6:02 at night. So from 6:02 a.m. to 6:02 p.m. on October 23rd, 1023 is considered National Mole Day. So let's talk about representative particles again. Representative particles, atoms are your elements from the periodic table. Molecules are your covalent compounds, something like CO2, NO2, C12H22O11. Formula units are your ionic compounds. So when you're looking at ionic compounds, if it's an ionic compound, it has at least 1 metal or it has 1 cation, and it's made up of cations and anions. So examples would be sodium chloride, iron 2 oxide, magnesium oxide. So what are the representative particles for each of the following? Let's take a look. So we're going to look at C2H6, okay? Well, that's made up of nonmetals, so that's going to be covalent compound. So our representative particle here is going to be a molecule. Okay, our representative particle here, we have metal, nonmetal, that's copper 2 chloride. That's going to be ionic, so that's going to be formula unit. And your representative particle here for copper is going to be an atom or atoms, okay? Because it's a singular element from the periodic table. So now this next question applies what we just learned. We know that Si is silicon, which is an atom, and we know it says, the question says, determine the number of moles. Well, we know that 1 mole of silicone is equal to 6.02 times 10 to the 23rd atoms of silicone. So what we're going to do is we're going to use that conversion factor. So when we look at a conversion factor, what we're doing is we're really multiplying this number right here by a number that's equal to 1. And if we put one thing on top, 1 mole of silicone on top, and 6.02 times 10 to the 23rd atoms of silicone on the bottom. Okay. Now, 1 mole silicone is equal to 6.02 times 10 to the 23rd atoms. So we are putting what's on top is equal to what's on bottom. So when the top and the bottom, the numerator and denominator are equal to each other, they cancel to equal 1. So we're not changing the value, the quantity that's there. We're just changing the units of what's there. So atoms cancel. That would be like x divided by x. So this is kind of like x times y divided by x. Your x cancels and you end up getting y. So we end up getting moles of silicone. Okay, so if we do that in our calculator, what we're going to do is we're going to do our 1.51 times 10 to the 15. So 1.51 EXP or EE, depending on your scientific calculator, minus EXP 15 divided by 6.02 EXP 23. Remember, the EXP is coding your computer or your calculator to be times 10 to the whatever you put in next equals, and this gives me a value of 2.51 times 10 to the negative 9 moles. And I want to ask myself, does that answer make sense? Well, this number is less than 6.02 times 10 to the 23rd. So I know that this number has to be less than 1, and it is less than 1. So this is going to be your answer here. How do you know what goes on top, what goes on bottom? What you want to get rid of, you start, these are your given units, and what you want to get rid of is your given units, they go on the bottom. What you want to go to goes on the top. So going back to our discussion of a dozen, here I can have a dozen limes and a dozen cars. That's going to be 12 limes and 12 cars. But does a mass of a dozen limes equal a mass of a dozen cars? No, they are very different masses, right? Toy cars or regular cars, they're still going to have a different mass. Okay. So a mole of carbon and a mole of copper, do they have the same mass? No. Carbon and copper has a much higher mass than carbon. Okay. But they both have the same number. They both have 6.02 times 10 to the 23rd atoms. So a mole has the same number, the same count, but it does not have the same mass. It's like saying, okay, count out a dozen pieces of cotton balls. Okay. Now count out a dozen pieces of lead. That lead is going to have a much higher mass, right? So in this case, a mole of copper has a much higher mass than a mole of carbon. So how do you determine the mass of a mole? We need to use what's called the molar mass. Molar mass is the mass of 1 mole of any pure substance, element and compound, or element or compound. So the molar mass is equal to the atomic mass. Molar mass is the mass per mole. Atomic mass, or AMU, is the mass per atom. Okay. So molar mass units is grams per mole. Atomic mass units is AMU. Okay. So again, AMUs are for individual atoms or individual molecules. Grams per mole is the mass for a mole of that substance. So when I'm looking at this, manganese on the periodic table has an atomic mass unit of 54.94 AMU. So one manganese atom has a mass of 54.94 AMU, but 1 mole of manganese atoms, so 6.02 times 10 to the 23rd manganese, has a mass of 54.94 grams. So let's look at some examples. 1 mole of aluminum is 26.98 AMU, 26.98 grams per mole. What about carbon dioxide? Well, carbon dioxide has 2 different elements, but it also has 2 oxygen atoms. So we have the mass of carbon, which is 12.01, and we have 2 times the mass of oxygen. So you need to multiply by the number of atoms. So 2 times 16.00 is going to be the mass for oxygen. And when I add that together, I get 12.01 plus 2 times 16.00 is 44.01 grams per mole for carbon dioxide. Now, where do I get these numbers? These numbers come directly off of the periodic table. What I would like for you to do is I would like for you to round to the hundredths place when you're doing these calculations. So let's look at this is copper 2 nitrite. Okay. When I'm looking at this, I have the mass of copper, which is 63.55. Then I have the mass of nitrogen, which is 14.01 times 2, because I have 2 of them. The 2 distributes here and the 2 distributes there. And then I have 4 oxygens. So 4 times 16. When I add all of that together, 63.55 plus 2 times 14.01 plus 4 times 16, that's going to give me an overall molar mass of 155.5 grams per mole. Again, a rule of thumb for this class, round your numbers from the periodic table to the hundredths place. Take a look at a few practice problems so that you have a better understanding of molar masses. So this first question, we have Cl2. Well, when I look on the periodic table right here, I have Cl, and Cl is 35.45. So I have 35.45, but I have 2 of them. So I'm going to multiply that by 2. And that's going to end up giving me 70.90 grams per mole. Next, I have potassium hydroxide, and I have potassium right here, and potassium is 39.098, so that's going to be 39.10, and then plus oxygen, which is 16.00, plus hydrogen, which is 1.01. And I'm just pulling these numbers directly off of the periodic table. So that's where hydrogen is, and this is where potassium is right there, and then oxygen is right over here. Okay, so when I add those together, I get 40.11 plus 16, so I get 56.11 grams per mole for potassium hydroxide. Okay, so for the next one, beryllium chloride, I'm going to look at beryllium, and beryllium is right here on the periodic table, beryllium chloride. So I want to figure out beryllium is 9.0122, so it's going to be 9.01 plus 2 times 35.45, which again is 70.90. So I end up getting 79.91 grams per mole. Our next one is iron 3 chloride. So iron 3 chloride, iron is 55.85, 55.85. And this time I have 3 chlorines, so plus 3 times 35.45, And I'm going to go ahead and calculate that on my calculator. And I end up getting 162.2 grams per mole. BF3, boron trifluoride. So boron is going to be right over here on the periodic table. Fluorine is right here. Boron is 10.81. And then I have 3 fluorines. Fluorine is 18.998, which rounds to 19.00. So I do 10.81 plus 3 times 19. 3 times 19 is 57 plus 10.81. That's going to end up giving me 67.81 grams per mole. Our next one is carbon, 2 chlorines, and 2 fluorines. And so we have 12.01 for our carbon plus 2 times 35.45. And eventually you start getting really used to these numbers. So I know that that number is 70.90. And then I have plus 2 times 19, which is 38. So I have 70.90 plus 38 plus 12.01, and that's going to give me 120.91. Okay. And then our last one is magnesium hydroxide. So magnesium is going to be right here on the periodic table, and that's going to end up being 24.31. 24.31 plus I have 2 oxygens, so 2 times 16 plus 2 hydrogens, 2 times 1.01. So I get 2.02 plus 32 plus 24.31. That's going to end up giving me 58.33 grams per mole. And hopefully that was helpful for you. Now, right here, I recommend you pausing this video and copying this diagram into your notes. This is the diagram that's going to help us convert from one type of unit to another type of unit. So say I'm at moles and I want to figure out how many grams are in those moles. Well, I'm going to multiply by this conversion factor. So I'm going to put my molar mass on the top and my moles on the bottom, because remember, molar mass is grams per mole. I want to go 2 grams, so I want grams to go on the top and I want moles to go on the bottom. When I want to go from mass to moles, I want grams to go on the bottom and I want moles to be on top, because I'm going from mass, which is going to be given to you in grams, okay? And I want grams to cancel. When I'm going from moles to particles, and remember, our representative particles can be atoms, they can be molecules, or they can be formula units. Okay, if I'm going to representative particles, I'm going to have my 6.02 times 10 to the 23rd particles on the top. If I'm going away from them, I'm going to have my 6.02 times 10 to the 23rd particles on the bottom. And then on the top here, this is something that we have not talked about yet, and this is going to be in our next slide. But at STP, standard temperature and pressure, 1 mole of any gas takes up 22.4 liters. So let's look at that. That's called Avogadro's hypothesis. Avogadro's hypothesis states that equal volumes of all gases at the same temperature and pressure contain the same number of particles. So when you do the research and you run an investigation, you realize that at STP, STP is standard temperature and pressure. At STP, 1 mole of any gas equals 22.4 liters. So 1 mole of any gas equals 22.4 0.4 liters, and that's your conversion factor. Now, STP is either 101.3 kilopascals or 1 atm. They are the same exact values. You just need to know that that's what standard pressure is. And standard temperature is either 0 degrees Celsius or 273 Kelvin, which again is the same exact value. Now, what I did here is I took that portion of the mole conversions and I just moved that over. So I moved that. I turned it a little bit so that you can see these conversions. So if I want to go from moles to volume or to liters, I put liters on the top. If I want to go from liters to moles, I put liters on the bottom. Okay, so these are some conversion factors that are going to be helpful for you. So let's look at a couple practice problems before we head out for the day. Here we have what is the molar mass of these different substances, and this will be helpful for you for your lab. So it's definitely worth writing in your notes. So calcium carbonate. Calcium carbonate is what makes up chalk. So when I look at calcium, calcium is going to be 40.08 on the periodic table, and I have one of those. So 40.08 plus carbon, which is 12.01, plus 3 times oxygen, which is 16.00. Okay, so I'm going to do that in my calculator. 3 times 16 is 48, plus 12.01 plus 40.08 is going to end up giving me 100.09 grams per mole. Now, copper, the molar mass, you just look on the periodic table. So copper, I go to CU on the periodic table, and I get 63.55 grams per mole. And then when I'm looking at this next one is going to be sugar. So you're going to be using sugar cubes in your lab. I'm looking at 12 carbons, 12 times 12.01, which I know is 144.12, and then plus 22 times 1.01, which is 22.22, plus 11 times 16. And at this point in the year, I usually show people the shortcut for 11 times anything in case you don't know this. 11 times anything, you split the numbers 1 and 6, and you add them for your center number. So that's going to be 176. Okay, so I have 144.12 plus 22.22 plus 176. That's going to give you 342.34 grams per mole. Now, another question, and this is not going to show up in your practice problems, but I really like this type of question, and it's something that we would teach in a typical year. What percentage of this compound is oxygen? So percentage is going to be, so your percentage is your part divided by your whole times 100. That's what a percentage is. Percentage, percent per 100, okay, percenty. So if you look at that, your part of oxygen is this 11 times 16. So we have 11 times 16, which we know is 176, divided by the whole, which is the whole mass, times 100. Okay, so this helps us. This is called percent composition. So 176 divided by 342.34, and that's going to end up giving you times 100, 51.41% of the mass is oxygen. Okay, so your next question is, given 5.43 grams of C12H22O11, calculate how many moles of the compound there are. So if I'm going to look at that, I'm going to do 5.43. 5.43 grams of C12H22O11. And I want to follow what we would call in class the mole road or the mole highway in your notes. So grams goes on the bottom because I want to get rid of grams and I want to go to moles. So how many grams per mole? It's 342.34 grams per mole. So I do my 5.43 divided by 342.34, and that's going to end up giving me 0.0159 moles. And I want to answer in 3 significant figures because I have 3 significant figures in my given question. Okay. Now, here's the thing. It says moles of each element. Well, I would take my answer, my unrounded answer in my calculator is 0.01586114. Okay. And I'm going to, if this is my moles of C12H22O11, well, I'm going to do times 12 moles of carbon for every 1 mole of your compound, C12H22O11. Okay, so if I wanted to figure out, so that's for carbon. If I wanted to figure out for hydrogen, I would multiply by 22 because there are 22 moles of hydrogen for every 1 mole of compound. And if I wanted to do oxygen, I would do times 11 because there are 11 moles of oxygen for every 1 mole of compound, C12H22O11. Okay. And then your last question here, how many moles are there in a 43.5 liter sample of hydrogen gas at STP? Well, remember, we have 43.5 liters. That's our given. We always start with our given. Okay. Our given and then times our conversion factor. Well, what conversion factor do we have? Well, I know for every 1 mole at STP, it takes up 22.4 liters of gas, okay? And that was my conversion factor in our last slide. So 43.5 divided by 22.4, that's going to end up giving me 1.94 moles of hydrogen gas, which is H2. And that's going to be your answer. So a couple of things. When you're looking at these problems, you always start with your given. I'm going to put this up on the top of the screen. You do your given times your conversion factor. And whatever your given unit is, your given unit goes on the bottom. The unit you're trying to go to goes on top. Sometimes you could have multiple step problems where you're going from one given to there's like a stopping point. Okay. So say I wanted to go from particles to grams. I have to go through moles first and then from moles to grams. Okay. So particles to moles, moles to grams. Hopefully that was helpful for you. It is confusing, it is challenging, but it definitely is something that takes a lot of work. And when you practice it, practice makes progress in this situation. So the more you practice, the better you will get at all of this.